and we are now committed to revive this collaboration and finding new ways. He's visiting IFISC, he's staying in room 105, and he will be there until Friday, and he's willing to discuss about nanoscience, the subject of his talk today, or genetics and statistical human genetics also. So you're welcome, and I pass you the word.
Yeah, thank you, Ernst. Thank you for the invitation. A very interesting place, and let me tell you very briefly about my island. It's Iceland. Well, not about geography, because that is very important. I don't want to spend time with that. My school is called Háskólinn Reykjavik, which literally means high school of Reykjavik. So you see some relation with English. So it's Reykjavik University. It's relatively new, approximately 10 years. And it's the second largest in Iceland. The first one is a state university, the University of Iceland. That is called in Icelandic Háskóla Íslands. And then our university, let's say, is second, but it's half private, half state funded. And this picture here is the logo of my school. I am in the School of Science and Engineering. There are several schools. It's a business school. Then it's a law school, a computer science school. And this represents the new building, or let's say a schematic description of our new building, where we moved in 2010. And now, if you look, the picture in reality was not full, or the plan was not a complete ring, and in practice it's only something linear. And we hope, but that is for the future, there will be other parts. So you see, observe the architecture looks like a pizza. But if you look from here, so there is a nice center, so it's the sun and planets and other astro bodies. And this is the sun, and you see the sun from the ground. It's a nice large cylindrical round hall where it's also possible to have large meetings, and only in glass, so you see nice outside. And now there are two wings. This is Venus, and the other side is Mars, so I live in Venus. And then the opposite is Uranus, where we have a nice library. And that's all for the moment. So in reality, yeah. But it's a nice place. Now here, just by our building, it is a piece of, let's say, a little beach and a little place where you can go and have sun, because sand in Iceland is black, it's basically ash. But this is imported, and it's yellow, and in summer day you have a lot of people coming there and enjoying the water, and there is even a pool with heated water. Now here on this hill, just up on the hill, there is a nice building which is something that I consider the symbol of modern Reykjavik, called the Pearl, which is 6 tanks which hold hot water. And on top of them there is a big roof in glass and a restaurant, and you can go outside and see the city. So the hot water is geothermal heated water, which we use every day. And my eternal joke is that there in Iceland we pay for cooling down the hot water and being able to use it, and not to heat it with warming, because it comes with 120 degrees under pressure. So that is not for free still. You have to, yeah. Okay, so I'm going to explain the how we work, what our work in our group in Reykjavik about open quantum systems, which are, let's say, in a very intense research. And my plan is to show only briefly the slides which have more technical content, and to show more examples, but the slides with calculations are mostly for my colleagues in nanosciences as reminders to continue different discussions that we've already started. But of course, anyone is free to ask questions. So the general idea is that we have a system, and I would like to call it a sample, and it is attached to two leads. Sometimes they are called terminals, and we can imagine there are some contacts. We can even imagine there are more than two terminals, and this is a regular setup that we are discussing. Now, we know how to calculate. We are talking about quantum mechanical behavior of electrons in this system, and we know how to describe a system when it is isolated, a quantum box. And we know how to calculate wave functions. We know how to calculate wave functions even if the system is infinite, some plane or some. But we do not know how to formulate the problem, or we do not know how to calculate wave functions when we have different systems in contact. Because we know the wave functions here, we know the wave functions here, we know the wave functions here, but what will happen when they are put in contact? And of course, there might be other solutions, but our approach is to use a statistical operator. So simply speaking, the wave functions that we know an electron will experience in the system will actually not be known. I mean, we know the spectrum, but we know which one is the wave function. So we have to describe statistically or have to point to calculate the probability of occupation of each particular state. So this is the role of the statistical operator. And now you have an equation for the statistical operator, but once you have the statistical operator, you can calculate mean values. So any observable will be calculated, and the mean value will be calculated by taking the trace over all states of the statistical operator multiplied with that particular operator attached to the observable. So we would like to calculate the charge density in the system, in the sample. We would like to calculate the current density. We would like to calculate the current in the left lead, in the right lead. In equilibrium, we expect the current through the sample will be zero. That is, what is going in is going out. So all these properties we need to approach through the statistical operator. Now, the statistical operator generically satisfies an equation which is sometimes called Liouville von Neumann. Liouville is the classical version. And we know to write down this equation generically for the whole system. Two leads and the sample. Put together, they have a statistical operator. But we would like to define a statistical operator of the sample alone in the presence of the leads. If the leads are taken away, we know what to do. But if the leads are there, then we have to define how the statistical operator of the sample looks like and write an equation for that. So what we need is to average over all degrees of freedoms of the leads. So this is written here. The statistical operator of the sample is a trace over the left lead, right lead, and the total statistical operator. So we have Hamiltonians for the sample, left lead, right lead, and we have a Hamiltonian corresponding to the transfer of particles from one to another subsystem, which are given by annihilation and creation operators in the sample and in the leads, and reversely. So they describe the transfer through the contacts. And we assume the leads are in thermal equilibrium. They are big reservoirs. They are described by Fermi functions. And we need to see how can we produce an equation for the so-called reduced density operator. The reduced density operator meaning the one describing only the sample where the leads are averaged. So to do that, the known technique is called Nakajima-Zwanzig projector method, and it has been used, to my knowledge, initially in quantum optics, and now since mesoscopic transport is studied, is adopted in our field. So originally, let's say, or in quantum optics, the transfer Hamiltonian is our transfer Hamiltonian is the electron-photon interaction, and the leads are replaced by the photon bath. Sample may be usually an atom, and now what is being done is that the average of the lead or the averaging over the lead degrees of freedom is denoted by the operator P called projector. We normalize it with a leads distribution function. So the square of P is P itself. That's why it's called the projector. And then we define the complement of the projector, 1 minus P. So if we use P and 1 minus P, that is Q, in the Liouville equation for the whole system, then we are going to split this equation in two. Because we are after an equation satisfied by P rho, the projection of rho on the sample. So we need to eliminate the complement. So now, with more or less formal manipulation of these operators, we can separate our initial Liouville equation into two. And here we have to eliminate what I denote here Q rho. So the complement of the projector. Then there are several possibilities to do that, and I'm going to use the simplest one. So after some, as I say, algebraic or formal results, we have two equations. Q rho time derivative is related to Q rho, but there is another Q here. So this, let's say, Q abstract operator behaves in a sense like a small quantity. Because if the coupling between the leads and the sample is not very strong, we would say P being a projector is not very far from 1. And then 1 minus P would be, let's say, simply speaking, something small. So we can say, what if we neglect Q versus 1? Then we can build an equation only for Q rho, a time-dependent equation. And here we have again Q rho. And this is something that we can interpret as a term, which if we take it away, it's a homogeneous equation. If we put it back, we can find the solution through the solution of the ordinary differential equation with an extra free term, which is here. And after that, we are going to replace Q in the first equation and have a lowest order equation for the whole density operator projected on the sample. So this is the master equation that we are looking at. If now we write it in a, let's say, more explicit form, we get now the density or statistical operator of the sample alone, where the leads are included through an average. It is a commutator which is familiar from the Liouville equation for a free or isolated system, plus the contribution of the leads with the, through the transfer part. And you see, it's not, doesn't look very nice. Observe that the transfer part occurs in powers of 2. So this corresponds to the fact that the electron goes both ways between leads and sample. And the statistical operator is under time derivative, it's under this commutator, but it's also under an integral. And now, extra assumptions are being done usually in optics, which are called Markov approximation, to say that the time evolution of the statistical operator, at least in the case of electrons in interaction with photons, is relatively slow, so you can say it is constant during the integration. So that's an extra approximation that we are not using, but at least in some cases we could. But, so in a sense, if the interaction of the electrons or the transfer of the electrons between the sample and the leads and reversely is very slow, which is equivalent to a weak electron-photon interaction or adiabatic limit, then we always can consider the Markov approximation. But as I say, we are not doing that. We are solving our equations. It's actually a matrix equation. We are solving by discretizing the time and doing discrete time steps, and we evaluate the derivative in both directions at the same time. So we calculate right and left derivatives and take the mean value to eliminate bias. And this is called the Crank-Nichols method, which is used in partial differential equation, in fact, whereas here we have only differential equation, but it is true, it is integral differential. So now the integration in time, if we do it in time steps, it is relatively easy. If we calculate it at this time step, next time we only add the increment. So it's going recursively. Now, we have to define the coupling. What we know how to do is to calculate the wave functions in the system or in the sample when it's isolated, and the wave functions in the leads when they are isolated. When we put them together, then we have to make an assumption. We have to define our transfer. So what is the probability that the electron is making, is transferred from one side to the other side? And then we need a model. So what we do is we assume that within the contact, although the wave functions for the isolated systems do not overlap because they are calculated for the closed system, so at each boundary they vanish. But then here we have an ansatz and we say, okay, here we have a kind of kernel which combines the values of the wave functions in the contact region. So this is an empirical, phenomenological, or some fabricated ansatz, to describe, and I agree, this can be a part where there can be, yes?
I have a question. If you have a normal sample and contact leads, so if you would go from a system where you have metal-like leads and a semiconductor sample, for example, you would get effects like a Schottky effect at the boundaries.
Yeah.
And so here you're looking how the wave function would merge, then it would be isolated. But considering that the systems don't change themselves when you connect them, and what do you take into account?
Yeah, so we can only say that this type of effects are taken into account by a simple one parameter. But I agree, if you want to make a more elaborated description of the contact, that is, of course, possible. Yeah. So this is, let's say, one description. We sometimes use a discrete version of our system, which is even a further simplification. In this case, the two parts, the leads and the sample, they have just one contact point. Of course, you can pretend they have more, but minimalistically, they will have one contact point, and then the transfer will be a parameter, and the wave function in the lead at the contact point called 0 in the lead, and the wave function in the system, in the sample, called phi, or the particular state, at the particular place where the contact is attached. So we can attach the contact everywhere. So this is basically our simplest version. And again, the transfer, the coupling relates one state in the lead with one state in the sample. So it carries two labels. At least in this case, we assume one channel in the leads. Now, because we work with creation and destruction operators, our density operator for the sample that we are going to find is a matrix. But it is a matrix in the Fock space. It is the Fock space, as you know, is a space where you consider fermions, or these are, of course, for the fermions, and all possible single particle states are either occupied or not. So here each 1 and each 0 corresponds to how many electrons are on a state. So these are basically manifold states. And then if we know the action of the creation and destruction operators, then we can build our matrix elements. And now, very briefly, we also want to include the Coulomb repulsions of the electrons inside the sample, which in this framework is, let's say, relatively straightforward. So to our sample Hamiltonian, we have to include the Coulomb interaction, which is written here in the second quantization, and we have to be able to calculate matrix elements of this operator in our Fock space, which I used to call bit strings. And because the system is open, then we can have all combinations from 0, 0, 0, so no electron in the system, in the sample, up to 1, 1, 1, 1, that is, all states in the sample are occupied. So we have to make combinations of these states, and we do linear combinations, and we find the eigenstates with Coulomb interaction included, and this is a method which is regularly called exact-diagonalization. So now, if we want to calculate current through the system, we assume what is called the electric bias. The chemical potential in the left lead is slightly higher than the chemical potential in the right lead, so this energy gradient or potential gradient creates a current. The electrons are going to travel through the system, and they are going to use the states which are in between the mu left and mu right, which we usually call the bias window. The states which are in between or within the bias window, they are the states which would contribute to the transport. The states which are below will be occupied. If we start with a sample which is empty, and then we attach the leads, then first thing that will happen that the sample is going to absorb electrons, and then we will have transport. But now, because we have the Coulomb interaction included, we have to consider a diagram not of the single particle states, but of the chemical potentials, because the chemical potential is how much is the energy increasing when we add one particle. And then if a particle is coming in, then it will only be transported if together with the other particles they will give a state in the bias window. So what is now relevant is the scale of the energy shifts, the variation, the chemical potential, which is the ground state of the state with n particles minus the ground state of the state with n minus 1 particles. So now, one more element is that we can attach our leads, let's say, in time. So we have each contact described also by a time-dependent function. At the initial moment, this function is 0. So our setup is that we have a sample and leads, and they are not in contact. And this is t equals 0. And now we make a contact which is varying in time, in strength, from 0 to a certain value. So these are functions defined between 0 and 1. We can also detach the contacts, and I will show you examples with time-dependent contacts. So a simple example is we have lead left, lead right, and we have a sample which is discretized. So instead of having a continuous short wire, we discretize in space because we want to solve the states, we want to find the states in this simplified manner. And in this graph we have the chemical potentials when we consider the Coulomb interaction varying in a range. Now the Coulomb interaction depends on the positions in all space, but this is a prefactor. So I can say if I take a prefactor 0, the particles are independent. If I take the prefactor larger, I can go, there is no reason to stop to 1. I can increase the Coulomb energy and see what happens. And let's say for 0 Coulomb, I have in the bias window, so this is a bias window, mu left, mu right, states corresponding to 4 particles. The ground state with 4 particles, because this is a chemical potential with 4 particles. It actually is a red line which shows the charging when I attach the leads and increasing the contact strength gradually in time between 0 and 1. So then you see we have approximately, it's not 4 but 3.6, because this chemical potential in the bias window tells you that there will be something between 3 and 4 particles, and the current is after the initial charging, the current is in the left lead and in the right lead, they are equal, has a certain value. Now if I consider the Coulomb interaction 0.3, then I will have no state in the bias window in this interval. Then, correspondingly, the current, the green curve, in long time will drop to 0. So the sample will charge, but then as soon as it's charged, there is no state. So this is Coulomb blockade. In Coulomb blockade, in this description, is nothing but the situation where you have no state in the bias window. Now, it is called Coulomb blockade because this is, let's say, it is not necessarily specific to system with Coulomb interaction, but usually the spacing is larger in the Coulomb.
Yes, so the red lines are calculated in the absence of transport, right?
Say it again, please.
The red lines, yes, they are calculated in the absence of transport. Or
these are chemical potentials.
These are the chemical potentials.
They do not depend on the transport.
Yes.
These are in the, exactly, in the leads.
You can maybe calculate them in a self-consistent way, including transport. So I mean, you are comparing something that is not in a transport situation with something that is within a transport situation.
The chemical potentials are in the leads.
Yes.
And then I'm not comparing. I'm looking at the current in the leads and charging of the sample. But whether the current flows or not, or whether in the steady state I have no current or very little current or more current, to me it doesn't mean that there will be different chemical potentials in the leads. That's what you mean.
Yes, but I mean, in a way, the red lines just help you to interpret this result in the presence of transport. But you can also calculate the chemical potential in the dot, including the transport.
It's not chemical potential in the dot.
Well,
it's in the leads.
No, the red lines.
Yeah, the red lines are the chemical potentials. Okay. This, I agree. Yes, these are the chemical potentials in the dots. These are the chemical potentials in the leads.
The blue ones.
Yeah.
Yes. Well, but I think that maybe in the sequential tunneling, this is okay.
Yeah. Okay, I understand what you mean. Yes.
But the question is, if you recalculate your red lines increasing the bias window?
No, they don't depend on the bias window. The red lines are simply...
This is finite equilibrium.
On the other hand, you have to understand the red lines actually are not included in the calculation, in the transport calculation. They are only for illustration.
Yes.
I mean, the states which exist in the bias window are only, let's say, I'm looking at those just to understand the transport, but they are not in the equations. Yeah. Okay, we can also look at evolution of the states with a fixed number of particles. I'm going to skip that. But now I would like to show you a more complex situation. So in this example, I have now a longer, call it quantum wire. I have 10 sites. I define it in 10 discrete points. And now I have the left lead fixed, attached to the site 1, to one end of the system, and the right lead can be moved. So imagine the right lead is the tip of the scanning tunneling microscope. So I would like to look at the current with one electrode fixed and the other one electrode exploring different sites. That is the goal. And we fix chemical potential in the leads, let's say within this window, and yes, we observe the chemical potentials in the sample. We would expect transport carried by 2 particle states and 3 particle states, and we look at the charge in the sample, and we look at the currents in the leads when the contacts now are oscillating. So in addition to the fact that the contacts one can be mobile, I can also do both mobile, but in addition to the fact that, of course, the right contact is fixed in this graph, in this example, but then the contacts actually switch on and off, alternating. So we have these oscillating currents in the leads, and the charge density in the sample is represented here, let's say on the average, because that will fluctuate. And what we obtain, or what we are looking at, is the propagation of the charge now in this graph, in this animation, you see the charge excess relatively to the background charge. And these are the currents. And we like to call this situation or this charge evolution standing waves. Now, one contact is at site 1, the other contact is at the opposite site, so number 10. So observe that we see nodes, antinodes. Now, they are not very harmonic. There are higher harmonics already in these oscillations. The currents look like almost like sinuses, but in a Fourier analysis they show also higher harmonics. And of course, depending on the placement of the second electrode, the mobile one, we can get different amplitudes. So in the first example we have these amplitudes. Now if we put the second contact at the site number 8, then we get a different amplitude of the current. So let's say this is consistent with the idea that you place your site, we placed our contact closer to a node than in the previous example. Of course, you may not see here very well the amplitude, but you see the amplitude in the currents. So we called this model the quantum flute, because, of course, in a musical wind instrument you have this type of standing waves, but of course this is only half a joke. And then
how will you do experimentally this the lower row, the alternating the contacts? How do you do this?
I mean, at the contacts, people put barriers and put voltages and gates, and this can be increased, decreased.
You have a physical value for the time unit?
It's the physical value, of course, it depends. I mean, the time unit is more of an intrinsic aspect. It also depends on the tunneling, the transparency of the barriers, because those can change a lot the whole evolution. But at least in our scale, it's something like 10 picoseconds. It's a little bit short, but this is also for computational reasons. And then what happens if we replace our sinus pulses with square pulses? Then we excite a lot of higher harmonics. So in this example, the left lead 1, the right lead site 10, we have almost, let's say, almost square currents in the leads. But in this placement, for example, right lead is at site 3. Remember, we have 10 sites. Site 1 is always in contact with the left lead. Right lead is now on site 3. Then we can have very strange and very many higher harmonics, which is expected for a non-harmonic signal, but even if you can see some kind of negative currents traveling against the bias for a very short period of times. Okay, so now I have another example, number 3, with a double system. So remember, our setup is one sample with 2 leads, but we can put 4 leads, and we can cut our sample in 2 parts. But in this case, we still keep the Coulomb interaction. So the Coulomb interaction will be the coupling between the 2 parts. And then we have states with 1 electron in the, I call it quantum dot, but okay, quantum dot or small quantum wire A, and 1 electron in quantum dot B, or the other way. So of course 1, 1, but you can have 1, 0, 0, 1, and you have combinations. So basically each state is degenerate with a number of electrons. Remember, this is a system which does not have a fixed number of electrons, it's open. So we wanted to have something in the direction of this type of experiments where there are 2 quantum dots, but there is some tunneling between the 2 quantum dots, and there are positive and negative current correlations. Of course, it might be in a different sense that our results, but okay, let me show you quickly what we obtained. We turn on the contacts to each subsystem, which sample at different time moments. So at t equals 0, we do the contacts to the dot A. And we look at the evolution. It is in the beginning empty. Then we put the contacts and some electrons are going in. But dot B is decoupled. Dot B is coupled at an earlier time, at a later time, approximately when the dot A is in equilibrium. So then, of course, the currents are going to redistribute through both systems. So in this example, we started with, now chemical potentials will depend on 2 numbers. How many electrons you have in one, how many electrons you have in second. So this is 2, 0, 2 electrons in sample 1 or A, 0 electrons in sample B. So it was, the bias was selected such that such a state was in the bias window. And it was a conductive state up to this point. But when we switch on the contacts with the second, then of course electrons are going to redistribute. I mean, there will be electrons going out from dot A but entering dot B, because a state with 1 electron in one electron in the other one has lower energy than the state with 2 electrons in only one subsystem, because they are closer together, have higher Coulomb. So this state is actually like contributing very, very little. So the transport is now for a while done through the other states, but now in the end there is almost nothing in the bias window. So the 2 dots block each other. Whereas in this example here, we do approximately the opposite. We put the bias window such that it contains states with electrons in both. So then, after the initial charging, dot 1 will not conduct, because states like this do not need 1 more electron. So 2, 0 would be for dot 1 only. But then as soon as we open, then the system becomes conductive. So this is another example, and there are many other improvements that we would like to do, but I'm not going to talk about that. Now, a more recent addition to the setup are photons. So we want to have this experiment. we have our leads, we have our sample, and in addition to that, we would like to have photons incident on the sample during the transport. And to simplify, we only consider one mode. We think that this is a cavity mode. And we can have the photons polarized in two ways, either in the transport direction, which is x, or perpendicular, which is y. Then we are including the photons in the description of the sample, like is being done regularly. Just consider the dipole approximation. The photons are described by a vector potential which is uniform in space, and then we shift the momentum of the electrons, and we get a Hamiltonian for the electron photon, and we consider another parameter, the electron photon interaction strength, which is something relatively complicated, but in a cavity it might vary. And then we consider also what other people may not consider, the vector potential to the square, which has some interesting effects. I'm not going to explain everything, but now to calculate the states in the sample, we simply have to combine electrons with photons. For the electrons, we keep the Coulomb interaction in the problem, we find the states with Coulomb interaction, and then we make the direct product of this Hilbert space with a Hilbert space corresponding to one photonic mode. That is a number of unspecified number of photons. So then we rediagonalize our Hamiltonian in these spaces. So then we have captured the interaction between electrons electrostatically and the interaction between electrons and photons and back to electrons in a almost quantum electrodynamic style. So, two remarks. The number of electrons is going to be a good quantum number. The photons are not going to change the number of electrons, but the number of photons will not. The number of photons will be known on the average, because electrons may absorb or may radiate. So, if we look at the charge, now we repeat the same experiment. That is, our sample is with photons, we attach the leads, but the leads are attached in time. So it's a time function, almost like a Fermi function, a step function. And here we see the charging. And there we see the number of photons, assuming initially we had 0 or 1 or 2 or 3. So if we start with 0 photons, we see that the electrons start creating photons. Of course, the numbers are small, and let's say these calculations are in the beginning. We expect to expand to larger number of electrons. Now, in transport, we can see that, if the photons are polarized perpendicular to the transport direction, nothing impressive happens, at least for this set of parameters. But if they are along the transport direction, the polarization, then if the coupling strength is large enough, so in this case, let's say a tenth of the typical gap between the electronic states, then we have a strong effect on the current. So these currents in the left and in the right lead, they correspond to perpendicular polarization, and these currents in the left and in the right lead correspond to the longitudinal. So it is like in this direction, photons act like a brake.
In the previous model, how you can distinguish between the two different polarizations?
So we simply have to define the polarization in the Hamiltonian.
Yes, but it's not here.
It is, no, I mean, the polarization is selected, it's an input. So in experiment, you say the photons can be polarized one way or the other way. So it is an input data. Okay, so this is another example, but this is special because it is not with leads. I wanted to mention this, but I probably will stop. Yeah, do I have 10 minutes?
3 minutes.
3 minutes. So it's an example which I like because it is now related but slightly or more or less different. Now let's assume we don't have leads. But we use the same idea. We have to solve the equation for the statistical operator. And then instead of photons, quantized photons, we are going to have a classical electromagnetic field or shining or a laser pulse on the sample. And now the sample is a ring. And now the ring has an important property, a spin-orbit interaction. So this is a new situation. Of course, I should describe it separately, but in this context, it is that we induce time-dependent currents. The pulse, the external pulse, is just something which depends on time and vanishes very fast. What we observe is that the system is left with a current which may not attenuate in time. It's not in a steady state. Conditioned by having in the system the two types of spin-orbit interaction. The two types are Rashba and Dresselhaus. So we need both. Rashba does, let's say, I like to say that it's like you look at the moon from the Earth and you always see one face. So the spin is going to rotate and it's always tilted the same angle, either outside or inside. But if Dresselhaus is considered, which is specific to the bulk and to the asymmetry of the crystal, but is very related, then the precession will be such that it has a negative sign relatively to the orbit. So if you combine this motion with this motion, you get basically two different frequencies. And the spin is going to create nutations and give us this beating effect, and actually is creating charge instability because it's related to the charge current. If one of the two spin-orbit interactions is suppressed, then we have charge current, we may have spin current, but it's constant in time. The oscillations come from the interference of these two. So this is another system where I would like to work more and include Coulomb interactions and other aspects. And this is also interesting that in this case the ring does not have a uniform charge. And this is also interesting to see what happens into a system with a finite width. But I'm going to stop here. So we have, let's say, many open problems. I mean, we can describe the evolution of open nanosystems, of course, with these limitations. So the one limitation is that we have only the lowest order in the coupling, and we miss effects like co-tunneling. That is something we would like to include. But compared to systems to other examples where co-tunneling is included, we have a system which has a shape in space. So we can look at geometry effects, geometrical effects. Coulomb blockade typically is considered for quantum dots. So in our case, we want to have space arrangements of the electrons and possibly spin. Spin is an evolution. We include the spin now. And we need developments of the electron-photon and possibly electron-phonon interactions. And as I discussed with the two-sample system, then I would be very interested to see how the coupling or possibly if we can describe drag effect, how that can be influenced by the presence of light. So this is okay, and the thermoelectric transport, which is in plan only in this approach. That's all I. So these are the contributors. This Vidar Gudmundsson, my research partner for 20 years, is Valeriu Moldoveanu, who did a lot of calculations with the GME. He was a driving force in the athletic part. And then it's our friend from Taiwan, Tang, is Kristin Torfason, my PhD student from Reykjavik, Olafur Jonasson, who is a master student now, who's going to US was a PhD, is Catalina Marinescu from Clemson, Marian Nitze from Bucharest, and me. This is the last slide when I show you how I explain to my students Coulomb effects in quantum wires.
So as usual, first questions are reserved for students. No question from students, and from the rest of the audience.
What is this kernel coupling the leads with the sample? What will you put in this J? Here.
So this is the simplest description that we could imagine. And again, this is something we may want to improve. But okay, maybe it's not a good idea to start with this picture. Maybe we look at this picture. So if we agree that we may, at least mathematically, describe our system discretized, because discretization is a regular strategy to solve differential equations, even Schrödinger, or partial differential equations, then we think in sites. So then the simplest description of a lead would be just a row of points, one dimension. So in this case, it's probably, it cannot be anything simpler.
It has a tunneling amplitude.
Yeah, the tunneling
In this case, I was asking about the other.
Yeah.
You should
No.
specify some spatial part.
Exactly. Now when we go to the space or more space resolution, then we can do that, because of course now there is a little difference between this actually in this discrete representation. The wave functions do not vanish on the boundary. They vanish on the next side, which is not included. I mean, you have a non-vanish, because you do not solve here the Schrödinger equation in a closed system with vanishing boundary conditions. You have a tight-binding Hamiltonian, and you can say the electrons, they vanish, the wave functions vanish one step outside your lattice. So in this sense, we already have here a kind of contact region. So our wave functions vanish here. So here, in this example, we need to come with an overlap model. So what we say, okay, we invent a space distribution kernel with a space distribution which is going to couple these wave functions. Let's say a sort of matrix element. If this is a delta, then the coupling is 0. If this is not a delta with a, let's say, a Gaussian, then we create a coupling. But I agree, this might look not very natural, or
At least you should specify more than anything. So,
yeah.
so in the other case, you have to specify one number, and here
You have to specify more, exactly. But it's, yes, as I say, it is, or in other words, to my opinion, it's no, I mean, you have to have a model of the compound. That is, in experiments, there are so many possibilities that, of course, modeling the contact in particular may be a totally separate work.
can you compare with experiments on relaxation of current, for instance?
Yeah.
I mean, this technique allows you to predict the relaxation.
Yeah.
When applying time-dependent voltage or steady voltage.
Yeah, there are. I mean, I don't have here, but yes, there are experiments on, but not as, not like the ones with, or at least I'm not aware of experiments with oscillating contacts of this type in space. But I am aware, and we did compare with experiments. There are some Japanese groups. They did time-dependent through quantum dots and relaxation measurements. Yeah. All I actually know is that accessing collective modes in transport is in general a problem in experiments, and this is where we want to point. That is, I mean, such experiments, in reality, these are collective modes.
Is there any chance to apply project theory or any other analytical treatment?
We did try, but at least in this case, because we start by co-coupling, then it's the evolution is not periodic. I mean, project theory is appropriate when you have a periodic evolution. And I agree, it can be used, for example, after a number of periods, and you say, yes, but no, we don't do it systematically. But I know what you mean. So our approach is to look at the time evolution, even if it is not periodic. And in general, with Floquet theory, if it's more than sinus, then, of course, having higher harmonics is a problem. Crank-Nichols, also my student, did his master with scattering calculation, basically with Floquet theory.
Okay, let's time to speak.